Welcome to the dynamic front of the Swiss Alps. In this video we reveal the regional structural framework of the Central Helvetic Fold-and-Thrust Belt, bringing its major thrust zones virtually to life through the first fully 3D structural model built with cutting-edge open source tools. This overview sets the regional stage. Detailed interpretation and step-by-step structural explanation of the model are available in my other dedicated videos linked below. The Helvetic Fold-and-Thrust Belt, shown in green, forms the thin-skinned frontal wedge of the Alps. It represents the formed sedimentary cover of the European margin, thrust northward onto the Alpine foredeep during collision. This overview places the Central Helvetic Belt within its broader Alpine context to set the stage for the 3D structural insights. Highlighted are the internal Penninic basement nappes, the external Gotthard and Aar Massifs, the Helvetic Fold-and-Thrust Belt, the Penninic sediment cover thrusted northward over the Helvetic Belt, preserved today as Klippen, the thrust blocks of foreland and the flat-lying morass basin. Helvetic sediments originated in the continental margin basin south of the Aar Massif and were thrusted over and across onto the North Helvetic Flysch along the Helvetic Thrust. Alpine tectonic forces folded these rocks into nappes and thrust sheets at depths of around 10 kilometers. And this subjected the rocks to increased temperatures, slight metamorphism and clastic-to-plastic reshaping. Using a 200-meter digital elevation model from the Federal Office of Swiss Topography, we reconstructed the Helvetic Thrust across more than 300 kilometers of the Alpine system. From the Rawil Depression in the west to the Rhine Valley Transfer Zone in the east. We also outlined the basal thrust of the Penninic units that override the Helvetic nappe stack and today appear in the north as Klippen. Our detailed 3D model focuses on the central section in front of the Aar Massif, a basement block uplifted through initial upthrusting and later isostatic rebound. This uplift goes together with large-scale thrusting in the morass basin and intense re-deformation of the emplaced Penninic nappes, contrasting with the region west and east of the Aar Massif, where Penninic and Austro-Alpine units advanced further north. Today, the Fold-and-Thrust Belt rises gently eastward by about 2 to 4 degrees, progressively revealing deeper structural levels. Let's explore now the Helvetic Thrust, a remarkable geological feature where the 10 km thick stack of Helvetic rocks was pushed 30 km northward. At its trailing edge, the sharp, narrow planar overthrust is visible for several kilometers, offering a vivid window into the immense displacement it represents. Helvetic sediments have been thrust over the Aar Massif and lie today on the deep marine turbidite of the Flysch basin, sediments sourced from the rising Alpine mountains. Let's close in north of Mount Titlis, where that displacement zone is beautifully exposed and the tertiary Flysch containing thick turbidite sandstones are overthrusted by Middle Jurassic quintine limestone along a knife-sharp, narrow overthrust. Turning now eastward towards Hahnen, the Helvetic Thrust can be further studied in detail. Along the thrust zone underneath the Nappe stack, smaller thrust blocks of Quinton limestone can be seen imbricated as thrusted over the fleece zone. Along the Helvetic displacement zone, meter-sized budinage structures provide further evidence of the intense deformation. In the Mount Pilatus and Mount Rigi region, the frontal part of the Swiss Alps are defined by the leading edge of the Helvetic overthrust, where Mesozoic carbonates are thrust northward onto the fleece, and coarse nagelfluh conglomerates of the molasse foreland. This marks the outermost expression of the alpine shortening, where thin skin thrusting transfers deformation from the alpine nut stack into the foreland basin. Ahead of the Helvetic front, the molasse foreland is broken into thrust blocks, pushed up by the advancing Helvetic belt and overridden by fleece, capturing the final pulse of the alpine compression. Let's now examine a major displacement zone which partitions the Helvetic Fold-and-Thrust Belt internally into two units. Traditionally, the Helvetic Thrust Belt has been subdivided into the axon Nappe, dominated by Jurassic rocks, with Cretaceous and Tertiary thrust structures appearing towards the east. And secondly, the Thrust Nappe, which forms the frontal thrust fold stack, composed exclusively of Cretaceous and Tertiary rock. Our 3D model, however, shows that the Jurassic part of the axon Nappe can be further subdivided. Its upper Jurassic section can be interpreted as the Jurassic core of the Thrust Nappe. This leads to a revised tectono-kinematic subdivision into two large thrust anticlinoria, each deforming independently into an amalgamated stack of recumbent thrust sheets composed of Jurassic, Cretaceous and Tertiary rocks. The formation of these two anticlinoria is controlled by the Schwarzhorn Shear Zone, which emerges as a key structure partitioning the Central Helvetic Fold-and-Thrust Belt. The Schwarzhorn Shear Zone forms a major deformation corridor within the Jurassic core, linking northward to the large-scale overthrust of Palfrey shales onto the Cretaceous part of the axon Nappe. Several Jurassic blocks appear as thrust sliver within the Palfrey shales, recording a complex overthrust zone. The Jurassic part of the Thrust Nappe, we call informally as the roadstock core, consists of several stacked thrust sheets forming a recumbent fold stockwork. Erosional remnants of this Jurassic thrust sheet shaped the striking red peaks of the mountains in the southeast. The Cretaceous section of the Thrust Nappe, here referred to as the Cretaceous slab, is detached from its Jurassic substratum along the thick Lower Cretaceous Palfrey shale zone. During this detachment, both the Cretaceous cover and the Jurassic core were deformed disharmonically. Structure within this part of the Schwarzhorn Shear Zone clearly record how early in sequence thrusting was later overprinted by a younger out-of-sequence event. Directly linked to basement thrusting within the Aar Massif that deformed and overprinted the earlier thrust sheets. The lower tectonic unit, the axon Nappe, features recumbent thrust folds of Jurassic rocks over-thrusting a tightly compressed Cretaceous inclinorium. Along the overthrust zone lies a chaotic melange of deformed Cretaceous rocks sandwiched in between, recording significant thrust displacements, structures clearly exposed in outcrop and revealed in Nagra boreholes and the Engelberg railway tunnel. For the full structural descriptions, outcrop examples, and an in-depth explanation of our 3D modeling workflow, please explore the dedicated videos linked below. These thematic chapters illustrate the anatomy of the Helvetic Thrust sheet, stockwork tectonics, deformational geometry associated with the Helvetic overthrust, structures created by local and regional shear zones, such as the Schwarzhorn Shear Zone forming the two mega anticlinoria mentioned earlier, and further the development of thrust sheets through décollement in thick shale unit and ramping up in hard competent limestone. As well as the characteristic tight recumbent ramp folds that build the Helvetic Fold-and-Thrust Belt. Thanks for watching. If you enjoyed this journey through the Alpine structure, give the video a thumbs up and subscribe to the channel for more exciting 3D insights into the geology of the Alps.